Yesterday you learned how to analyze exponential functions in the form f of x equals a times b to the g of x plus c. We learned to identify increase and decrease in intervals. We learned to identify the y-intercept. We identified the horizontal asymptote. We identified the domain and range. Today we're going to learn to analyze logarithmic functions in the form f of x equals log base b of some function g of x plus c. We'll start by graphing. I would ask you to stop the video and graph a couple of these equations, these functions, just to see. Graph y equals log x, graph y equals ln x, and go ahead and graph y equals log base 2 of x. If you'll stop the video and graph those real quick, and let's just see the general behavior of a logarithmic function. You come back, you will see these graphs all look very similar, but they're not the same. One thing I'd like for you to recognize, the calculator that you're using, the TI-84, doesn't do a very good job of showing the domain and range. Your calculator stops somewhere in here when it graphs this, but this actually goes to negative infinity. It goes down, never reaches the y-axis here. And the reason it never reaches the y-axis is because that's when x equals 0. And recall, the log base 10 of x is the power of 10 that gives you x. And so there's no power of 10, no power we could raise 10 to get 0, no power that we could raise 10 to get a negative number. Therefore, the domain of this simple logarithmic function is 0, not including 0, to infinity. Same goes here because this is the base e. E is a positive number. There's no power you can raise e2 to get 0 or a negative number, so its domain is also 0 to infinity. Same goes for here. Base 2 can't be raised to a power to get 0 or a negative number, so its domain is also 0 to infinity, and none of these include 0. So domain for all of these simple exponential functions is, simple logarithmic functions, is 0 to infinity, not including 0. The range in each one of these, even though this logarithmic function eventually grows slowly, it continues to grow forever. Remember, it's the power of the base that you would plug in to get this number inside. So if this is a very, very large number, then you would plug 10 to a very, very large number in to get that number. So this grows, but it grows slowly as we get larger and larger and larger with the x's. But the range in these functions is always negative infinity to infinity for these simple logarithmic functions that don't have some other function in here that's restricted, its domain is restricted. The range here in all three of these simple logarithmic functions is negative infinity to infinity. And because this graph approaches the y-axis but never reaches it, these graphs all have a vertical asymptote. Of y equals 0, x equals 0. X equals 0. That's a vertical asymptote. The logarithmic functions don't have a horizontal asymptote, they have a vertical asymptote. The exponential functions, recall, had a horizontal asymptote. They didn't have a vertical asymptote. So these are just some of the things that you can easily spot when you understand behavior. This is the general shape of a logarithmic curve. So let's look at for any function, because now we can take these and we can transform these. We can translate them left, right, up, down, and it changes all these things. So let's figure out where these x-intercepts come from. We'll figure out how to identify the domain and range. We'll figure out the end behavior. In this case, the end behavior, let's go ahead and look at the end behavior before we move on. The end behavior here, the right end of the graph is as x goes to infinity. And these are all three, y is going to infinity as well. As x gets large in the positive direction, y gets large in the positive direction. But now, one thing that's different from these than what we did before with functions, we don't have x going to negative infinity because we said the domain stops as x gets close to 0. So here we're going to say, as x gets close to 0, now remember, it's only coming to 0 from one direction. As x gets close to 0, in this case, your y is going to negative infinity because the graph's going down forever. In all three of these cases, certain transformations inside could change these. For instance, if you flipped it over the x-axis. But in these three graphs, you can tell easily from the graph that y is going to negative infinity. Well, you can't because your calculator didn't show it. One reason it gets so, it decreases so fast as we get close to 0 that the calculator can't pick that up and it can't plot the points that close together. So let's look and see at a couple of functions and let's see what happens here. If you were to graph y equals log base 3 of x minus 1, or g of x now is a little more complicated, but really and truly this is just a translation 1 unit to the right of log base 3 of x. And what you'll see if you graph this is a function that looks a little bit different in that it's not getting close to the y-axis now. Instead, it's getting close to x equals 1. Remember, we took the function log base 3 of x and we translated it 1 unit to the right. So the way that you can identify the vertical asymptote on these logarithmic functions is you take that g of x that's inside the log, set it equal to 0, and solve. So in this case, x minus 1 equals 0, x equals 1 is my vertical asymptote. That's also going to be the boundary for the domain. So in this case, the domain is going to go from 1 to infinity, not including 1. Remember, it would have gone from 0 to infinity if it had just been log base 3 of x. We shifted it 1 unit to the right, so it makes sense that our domain changes from 1 to infinity. Our range is still negative infinity to infinity. Our x-intercept, if we want to solve and find the x-intercept, remember we always find the x-intercept by setting y equal to 0. So in this case, y equals log base 3 of x minus 1. We set 0 equal to y. We have a logarithmic equation. We need the variables out of from inside the log, so we're going to convert this to exponential form. 3 to the 0 power equals x minus 1. That's 1 equals x minus 1. Add 1 to both sides and get 2 equals x. My x-intercept is x equals 2. Let's do another one. Let's do y equals, let's do ln of 3x minus 5 plus 4. So here, the first thing we'll figure out is our vertical asymptote. We're going to take the inside function, set it equal to 0 and solve. Add 5 to both sides. Divide by 3. And we get our vertical asymptote. It's x equals 5/3. That's also the boundary for my domain. Not including because it's an asymptote. My range is, once again, if you graph it, you'll see it's going to be negative infinity to infinity. Our x-intercept, this time we're going to set y equal to 0. And we're going to solve. This time, I need to get the ln by itself before I can convert to exponential form. So I'm going to subtract 4 from both sides. Now I'm going to convert to exponential form, and I'm going to take the base e raised to the negative 4. That's ln 3x minus 5. Oops, sorry, ln's gone. Just 3x minus 5. So now I'm going to add 5 to both sides. Then divide by 3 on both sides. I'm going to go over here because we've got a little more room. Get e to the negative 4 plus 5 over 3 equals x. That's my x-intercept. If we graph this one, our vertical asymptote is at 5/3. And we set our x-intercept e to the negative 4 plus 5 over 3. That's going to be 5/3, but it's a pretty small number. It's going to come up like this. And look like that. We can look at our end behavior on this one, and we'll do the one from before also in just a second. End behavior, as x goes to infinity, y goes to infinity, and as x goes to 5/3, y goes to negative infinity. In behavior on the one before, we should have done that before. Our vertical asymptote was x equals 1. As x goes to infinity, y goes to infinity. And this time as x goes to 1, y goes to negative infinity. And these are the ways that we'll analyze our logarithmic functions. And you can use these techniques to answer the questions on your Edge Elastic assignment for today.